Hello, welcome to the wonderful world of magnetic forces. Now, last time we looked at the direction of magnetic forces. This time we're going to be looking at the magnitude, or how strong those magnetic forces are. In other words, numbers. Alright, last time we looked at the right-hand rule. The right-hand rule, as the first box of your notes says, the first right-hand rule determines the direction of the force on a moving charge. Okay, so this box right here, that's what you're going to fill in there for it. Alright, so the rest of the slide is the breakdown. If you had trouble, you can go back to the other video. There's also a longer version of this video that really kind of goes through each of the directions and things like that. This video is just going to deal with our new information. So if you had trouble with the old stuff, you might want to go back. It's a few minutes extra in length, but it'll also review things with you. Okay, right-hand rule. If you set your hand up, you'll see that all of these work out. Velocity is to the right, so your thumb points that way. Magnetic field points out of the page, so your force points down. All right, magnetic field, that should all work out. All right, so we're going to be looking at the force and the charge. So we're in the next set of boxes, like what we see down here. All right, first box, equation. Our full equation, F equals Q, V, B, sine theta. So the force felt by the charge that's moving at a certain velocity in a magnetic field times the angle. Okay, so this is our full equation. We're going to break it down to all the little components. Okay, so this goes in the first box. Now, in the second little box, we're breaking down all the components. So the name is charge. The symbol is Q, and the units are C or coulombs, and or. Same thing. Okay, so that's our first variable in this equation. Our second variable, V, velocity. Name is velocity. V is the symbol, and our units are meters per second. Okay. B. We talked a little bit about B when we were dealing with, the bye-bye symbol. B is the symbol for the name of the magnetic field. This is new. You're going to want to really sit down and say B, magnetic field, B, magnetic field. Because it's not as easy to remember as V for velocity. Okay? Now the units for magnetic field is Tesla, or big T. Okay, so we have Q, V, B done. Now let's look at sine theta. Theta is the angle. So the name is angle, symbol is this theta. And our units, I didn't put it in here, but you can put them in as degrees, little symbol degree. Okay? So we're not doing them radians for those of you in calc. Okay, I'll give you guys a second to look at that. Okay, so we did Q, V, B. We've done sine theta. But that's a fairly complicated equation. I mean, it's got 5 variables. That's a lot. So let's simplify it down a little bit for our level. Those of you going into AP will have to keep that full equation next year, but the rest of us, we can really kind of simplify it down. Now, theta is the angle between V and B. So for example, if I have a magnetic field traveling this way, the angle between the direction that the charge is moving, so I got this little guy here, he's a charge, and he's going to start moving. The angle between the direction he moves and the magnetic field is your theta. Now, sine of 0 and sine of 180 both equal 0, which means that if your charge is moving either at 0 degrees, so same direction as the magnetic field, or 180, the exact opposite, it feels no force. Think about it as it's moving with the flow. It's not going to feel force, it's moving with the flow. Okay? So then your force is 0. But for the most part, we look at problems where the angle is 90 degrees. In other words, your charge is moving up, forming 90 degrees with magnetic field, or down, forming 90 degrees with magnetic field, or out at you, which also forms 90 degrees. Okay? And sine of 90 equals 1. Okay? So you have QVB times 1, which simplifies, which is what you're writing in this box, down to just QVB. The force felt by the charge equals QVB. Alright, so the right-hand rule deals with the force felt by a moving charge, but it also deals with the force felt by a wire with a current in it, because a current is just a whole bunch of moving charges. So this is kind of the same equations, but it has different variables because different things are involved. So let's look at the force on a wire in a magnetic field. So we're going to fill in the ones with the boxes with the dotted lines. Okay. So force felt on a wire in a magnetic field is ILB sine theta. Okay, so current, the quantity of charge. So how many of those little buggers are moving through it? Length. How long are they exposed to it? I mean, think about it. You know, the longer the wire, the more little electrons are in there. More protons, more little charges are in there. B, strength of the magnetic field, and sine theta. So let's break it down. First name, current. Symbol, I. Unit, A for amps. Second one, length, L. Units are meters. Third one, this new one again, magnetic field, represented by B. Units are T for Tesla. And in this case, our angle is between I and B, which is basically the same thing as V and B, because V is the direction they're going, I is the direction of the current, so the direction everything is flowing. Same thing happens if theta is 0 or 180, your force is 0. If it's 90, which it is most of the time, then your new one, which you can write in here, equals ILB. Okay, so if you're at 90 degrees, force equals ILB. That sine theta just equals 1. Now, let's look at some examples. So if you flip to the back of the page, we got a couple of questions. I'm going to work out 2 for you, then you're going to work out 1 for yourself. The 1 for yourself has an A or B, A and a B, but it's not too bad. Let's look at the first one. Now we've learned 2 equations. I'm going to use the simplified version. F equals Q, V, B, and F equals I, L, B. Now, we have a wire carrying a current, so we know that we're dealing with the force that has a current in it. So we're going to have 4 possible variables. F, I, L, B. So let's see what we can fill in. 2.7 meter wire. That's our length. Carrying 750 milliamps. Okay, this little m is milli, so that's times 10 to the negative 3. Alright, so it's 750 times 10 to the negative 3. If you have trouble remembering that, it is in your reference table. Now, for those of you who this will bother, which is me, and maybe some of you, this is the same thing as 0.75. Okay, that's your current. Your current is heading south. in a uniform magnetic field, okay, with experiencing a force, so your force is 3.2 newtons, and the direction is east. So we have a current to the south and a force to the east. We're looking for the strength and the direction of the magnetic field. Okay, let's give it a try. F equals ILB. 3.2 equals 0.75 times 2.7 times B. Plug it into your handy-dandy little calculator, and we're dividing both sides by 0.75. Oh, I meant to stick to red. 0.75 and 2.7 to get B alone. We got to divide both sides by it. So this one works out to be 3.2 divided by 0.75. And then we divide that by 2.7. We get 1.58. So 1.58 Tesla is the strength of a magnetic field. Now we're looking for the direction. This is right-hand rule. I is down, or to the south in this case. So thumb pointing to the ground. Your force is to the east. So put your palm facing east. Thumb down, palm east. Or thumb south, palm east. Okay, your fingers should now be pointing at the screen. Okay? So the direction is into the page, or you can also use X, because that's the symbol for it. Okay? Not too bad. Let's give the second problem a try. Two possible equations, F equals QVB, and F equals ILB. Now in this case, sorry, we can ignore this. This was the previous problem. So we're down here looking at this. We're at part B. Alright, the magnitude and direction of the magnetic force acting on a single electron moving westerly through a field at 7.89 times 10 to the 5th meters per second. Okay? So we have a single electron, so we have a single charge, which means no current. So we're using F, Q, V, B. So let's see what information we get. We're looking for the direction. Yes, we're looking for the direction and the magnitude of magnetic force. We don't know either of those. It's a single electron. Now, flashback to electrostatics. Q is negative 1.6 times 10 to the negative 19th coulombs. Is moving westerly through a field at 7.89 times 10 to the 5th meters per second. And it's moving west. Okay? Now, we do have the same magnetic field in this case, which is why it's part B. Okay? So it's 1.58 Tesla into the page. Alright, we have two directions, so our directions can be gotten. We have 3 of the 4 variables, so our force can be gotten. We're good to go. So let's start with the number. F equals QVB. So F equals negative 1.6 times 10 to the negative 19th times V. I'm really kind of worried I'm going to run out of space here. 7.89 times 10 to the 5th. And then this would go here, 1.58. I ran out of room. Okay, so we plug that into our calculator. And we get a force of negative 1.995 times 10 to the negative 13th. If you rounded that to 2 times 10 to the negative 13th, that is fine. Now we need direction. V is to the west. B is into the page, which is an X. Okay, so point your fingers at the screen. Your thumb pointing towards the left or the west. Your palm should be facing downward. Okay, so towards the south in this case. Okay. Don't stop here. I want to make something clear and a little bit different for you guys. I'm not really going to do this to you all that often, but this is an electron, which means your direction is not south, it's actually north. I know, we're all upset. But let me explain this for a second. If you remember, like when we talked about the conventional current with the right-hand rule, it was the direction that the positive charges would go. The right-hand rule works for positive charges. But the electron is a negative charge. So it's a net opposite charge. It's going to feel an opposite force. So whatever you find for the direction for anything, and it's an electron, you would flip it. So if you were solving for B, and you had the direction and the force of the electron, and you were solving for the magnetic field, whatever direction you get, you would flip it. You would use the opposite. The other way to do this, if you really hate that, is think about the right-hand rule being for positive and the left-hand rule being for negative. Because your left hand will give you just the exact opposite, so it'll all work out. So for those of us, including me, who are left-handed, it might be easier to remember that because left-handed people statistically die younger, which means that being the left-handed rule is a negative rule. It's bad. No, it's not really bad, but, you know, that's the way to remember it. An analogy. Okay? Now, you guys have a chance to try your own problem. So question 2, there are 2 parts. One is finding the value, the other is the direction. Now your version is different than others, so make sure you work it out for yourself. If you're still confused, there is the longer video that does a little bit more explaining with things, or you can just rewind and rewatch this. Good luck.